This video is on the bipolar junction transistor, and more specifically on modes of operation. The most important of which is basically the forward active mode, basically when we activate the device, and we activate it by forward biasing the base emitter junction and reverse biasing the base collector junction. So when we look at the band diagram here, we're going to apply a positive voltage to the base with respect to the emitter. As a result, we're going to reduce the field barrier that keeps electrons and charge carriers from diffusing. As a result, we're going to have an exponentially increasing number of electrons diffuse into the base. The base is so short that most of those electrons reach the other end of the base. But then we reverse bias the other junction. That means we apply a positive voltage to the collector with respect to the base. So the electrons that reach the other end of the base, they see a positive voltage and then they're swept across all the way to the collector. And this is activation because we've activated the device and we have the main current mechanism of emitter electron current that goes all the way to the collector. We can also have another mode, and basically we can forward bias the base emitter junction again, but this time we can forward bias the base collector junction. And what we see there is that if we forward bias both junctions by the same amount symmetrically, we're going to have diffusion from the emitter into the base of electrons, and we're also going to have diffusion of electrons from the collector into the base. And all those electrons are going to exit out of the base terminal. Since electrons flow in the opposite direction of current, what that means is that we're having collector current coming out of the collector, emitter current coming out of the emitter, and both of those currents are being fed by the base. So this is what we call saturation, and more specifically, I'll call this deep saturation because basically the BJT is no longer active, rather, and it's actually behaving like two separate diodes. But what we can do is we can apply an asymmetric bias, and by that I mean that we can forward bias the base emitter junction by more than the base collector junction. That means that we're going to significantly reduce the field barrier across the left junction, but we're not going to do much on the right junction. What that means is that we have lots of electrons diffusing into the base and across the base, and hardly any electrons diffusing from the collector to the base. Since now we have a much higher concentration of electrons on the other end of the base, they're going to cross and diffuse across into the collector. So what we're saying here is that we still have this device semi-active, and it's actually and a lot of the emitter electron current is still reaching the collector. So this is what I'll call light saturation. And I'll allow my devices to go into light saturation because they're almost like active. They're behaving almost like active, and that's what we see here, because we get most of the emitter current is actually most of the electrons in the emitter are actually reaching the collector. We also have another mode of operation, and let me remove markers here so we can be more clear, is that we can forward bias the base collector junction and reverse bias the base emitter junction. In other words, we can do the opposite of the forward active. But look at this. This is an NPN structure. So it's symmetric. If it is symmetric, if we forward bias the base collector and we reverse bias the base emitter junction, everything will work the same way. The only thing is that it'll just flip around. So now we're going to reduce the field barrier on the right junction, and we're going to increase the depletion width on the left junction. In other words, it's an NPN operated in the opposite direction, which is also NPN. So that's why we call it reverse active, because we're activating the device, but in the reverse direction. So, okay, we also have cutoff. Cutoff is when we reverse bias both junctions. And if we reverse bias both junctions, remember these are diodes, the currents go to zero. So the device is in cutoff because there's hardly any current going through the device in any direction. So if we were to plot this in a graph, here we have collector current and here we have collector emitter voltage. And in this region here is where we have a forward bias voltage across a base emitter junction, and the collector voltage is so high that it reverse biases the base collector region. So we get some sort of collector current. As the collector voltage changes, we get a slight variation in collector current, and that's the result of base width modulation. Now, when the collector voltage drops below the base voltage, we enter saturation, and this whole region here is saturation. And that means that in this region here, we forward bias the base collector junction, but the forward bias is so little that there's very little diffusion current. As a result, the device still behaves largely like an active device. This is what we're calling the light saturation region. At some point, the forward biasing across the base collector is so much that then the collector current starts dropping dramatically. What you see here is the collector current is going into the collector, but as it goes into deep saturation, it's going to zero, and at some point it can reverse. And that's why we see here that it goes all the way down in deep saturation. And when the collector voltage is zero, then the current is zero. Now, cutoff is when we reverse bias the base collector junction and the base emitter junction. And as a result, across that region, what we see is that the current is zero. So this x-axis actually describes the cutoff region. And now we can operate in reverse active mode. In reverse active mode, then we flip the device, and now current goes in the negative direction. That's why we have the collector current here. Now goes in the negative direction with respect to our original definition. One thing to note, however, and I'll remove markers here so I can highlight my meaning. When we design and build this BJT, we make the emitter junction, we make it very highly doped. That way we can provide a lot of charge carriers to the base that can go all the way across the device. So the device, although it is NPN structure that is reversible, it is not exactly symmetric. That means that when we operate in reverse active mode, when we forward bias the collector with respect to the base, the collector is actually lightly doped, so it has less electrons, so it is less effective. And that's why we see here that the current levels are not the same magnitude. So basically, in reverse active mode, the device is operating less optimally. And the forward active mode is when it's operating optimally, basically designed for forward active operation. Now, we've just described the NPN, but we can also have a PMP, and the same would apply. So in this case, we have back-to-back diodes. The back of a diode is the N region, and we have a PN junction here to the right, where the N region is the base, and we have a PN junction to the left, where it shares the same N region, the same back. So these are two back-to-back diodes. We're going to forward bias one junction here, and by doing so, we reduce the field barrier. And what we have is, then we have holes that can diffuse on over to the base. The base is so short that they keep diffusing to the other end of the base, almost all those holes. But then we're going to reverse bias the other region, so we're going to apply a negative voltage to the P side, and putting a negative voltage here, and we have a hole on this side, then that hole is going to get swept across on over onto the collector. So what we have in this case, and I'll remove markers here, it's the same operation except with holes. Holes are diffusing over onto the base. The base is short, so they keep diffusing to the other edge of the base, and there's a field that carries them across the collector region, and now we've activated the device with holes. The holes, since they're coming, they're actually flowing away from the emitter inside the structure. They're coming into the emitter here. We have an emitter current that is actually flowing into the emitter because it goes in the direction of holes. And then we have holes that are flowing out of the collector, so we also have a collector current that is flowing in the same direction of holes, and that collector current is flowing out of the collector. When we forward bias this region here, we also reduce the field barrier for base electrons to diffuse into the emitter. So that establishes another current component that flows in the opposite direction, and that's largely the base current that we have here. That in this case is flowing out of the base because electrons are flowing in the opposite direction of current. Okay, then when we quantify the collector current, well, the collector current is mostly just the whole emitter hole current that reaches all the way to the collector. Let me remove markers here. So it's largely just the whole emitter hole current. But then we have here, we have to account for base width modulation. So when the collector voltage is more negative here, it pulls away holes from the edge of the depletion region. And when that voltage is more negative with respect to the base voltage, then that means that electrons are also pulled away from the depletion region, and the depletion region expands. Expanding the depletion region decreases the effective base width, and as a result, we get more of the holes that reach the base leave the base to the collector, so we have a higher collector current. So this is the base width modulation. This is the base width modulation parameter, which we call early voltage. When we look at the whole emitter current that is actually reaching the collector, it's basically just the forward bias diffusion current across the base emitter junction. So what we see here is that this emitter current is nothing but a diode current. And that diode current is with respect to the forward bias of the base emitter junction. In this case, the base is N, so the forward bias is emitter base voltage, and that's what we have here is with respect to the emitter base voltage. And to reverse bias the base collector junction, we need to apply a negative voltage to the collector, and that's why we have here an emitter collector voltage instead of the NPN's collector emitter voltage. But if you notice here, this collector current is exactly the same as an NPN, except instead of electron current, we have hole current. And instead of a positive base emitter voltage, we have a negative base emitter voltage, which is why we use the emitter base voltage. Instead of a positive collector emitter voltage, we have a negative collector emitter voltage, which is why we use an emitter collector voltage here. Talk a little bit about symbols. In the NPN, we have here the NPN, and the one that is more highly doped is the one that is optimized as an emitter. So this is our emitter. We normally forward bias the base emitter junction, and we get current flowing out of the emitter. So we'll put an arrow to indicate that base emitter junction that is forward biased, and that's how we know that it's an NPN. The lightly doped N region is a collector region on the other side. So we have a positive base emitter voltage and a positive collector emitter voltage. We have current collector current flowing into the collector and out of the emitter. So we remove markers here, and then we can look at the PNP. And here we have the PNP structure. The emitter is the one that is highly doped, so that's the one that gets the arrow. Since current in the PNP is whole current, that is going from the emitter all the way to the collector, so current is flowing into the emitter, so that's why that arrow is flowing into the emitter. In this case, forward biasing the base emitter junction, we forward bias it with a positive emitter base voltage because the emitter is p-type. And to reverse bias the base collector junction, we need to apply a negative voltage to the collector, and that's why we use the emitter collector voltage. It's a positive emitter collector voltage here. Now the last thing that we can talk about here is capacitances. Well, whenever we have a forward bias, we have diffusion capacitance from the diode. And whenever we have a reverse bias, we have pretty much the depletion capacitance is the one that dominates. So if we forward bias the base emitter junction here, we'll get that the base emitter junction capacitance is a diffusion capacitance which is very high. In the forward active region, the base collector junction is reverse biased, so it gets a depletion capacitance which is a lot lower. As we transition into light saturation, then we forward bias the base collector junction slightly. So what we see is that we see a slight increase in capacitance, but not drastically. As we enter deep saturation, that's when we forward bias the base collector junction significantly, and that base collector capacitance then will start increasing to the level and to a point that it can reach the same forward biasing level that the base emitter junction has. So if I move markers here, what we see in the main point here is that capacitances for the base emitter and the base collector junctions are based on how they're biased and what voltages are applied to them. And these basically describe the different regions of operation for the BJT. I hope this was helpful. Thanks for watching.